Hello everyone. This video will demonstrate creating parent population and creating sampling distribution from gamma distribution from the previous scenario. So this is the previous scenario. In order to do that, we will generate random numbers from gamma distribution. Let's assume that the population of motor accident claims are about 1 million claims. Hence, there will be about 1 million random numbers to be generated. For this one, let's use set.seed function to make our random numbers reproducible. To generate random numbers from gamma distribution, we will use R gamma. So for this one, for R gamma, you need to put the number of sample that you would like to generate, followed by the shape. Shape, just now we already defined it earlier. So, sorry, shape equal to shape parameter, and as well as the rate, we also defined it earlier. Okay, so let's run this prompt. Now let's plot a histogram to see its distribution. So histogram population. So I would like to give the title for my histogram. Here, I use breaks equal 500 because I would like to have 500 bars. Okay, which bar? This is bar. This is kind of bar. So if I do breaks equal to 500, so there will be 500 bars. Okay. And then we try to run to see its shape. Let's zoom it. All right, so based on the histogram, we can clearly see a right skewed tail. So this presents a population from which we will sample. Okay, now let's create a sampling distribution from this population. For this one, let's simulate a 1000 different entries of each taking a random sample of 100 claims from this population. So means that first of all, we define the sample size. The sample size is 100 and the number of samples is equal to 1000. To do this, we will simulate using replicate function. Every entry calculates their own sample mean, which resulting in a collection of 1000 sample means. So run this command. Okay, so to ensure that our sample mean consists of 1000 observation, let's use length function. Okay, so 1000. Now, let's plot a histogram to see the distribution of our sample mean. Okay, so based on the histogram, the distribution of the sample means portrays a bell shape, which is normally distributed. So now let's check the moment of the sample mean. First of all, we will check the mean of the 1,000 sample means that we generated just now. So mean of sample mean. So our mean of the sample means here give about 1,199.221, which is close to the theoretical mean just now, which is 1,200. If you still remember this one, the one that you generated earlier, this one, the mu and sigma, this is actually the theoretical mean, the mu. If you cannot remember what is your mu value, just so the mu is 1,200. So our mean of the sample mean is very close to our theoretical mean. And okay, so let's do like this to make it our output readable and understandable. Okay, so print and paste function, mean of sample mean is, this is the actual. So this is the actual since, mean, oops. Mean sample mean, okay. And then print paste for theoretical, the one that you generated earlier, which is your mu, right? So put it your mu here. Oh, sorry, unexpected extra for, okay. Let's detect this one. It's bar. Oh, okay, extra. Okay. Okay, let's do one more time. Okay. So, all right. Oh, the value is okay, we can round off the value. Okay, you can round off. Okay, just round off the value. Okay, that is for the mean, sample mean. And now let's find the value. Let's calculate or check the value for the standard error. So standard error is equal to the standard deviation of the sample mean. So standard error of the actual that you have for the 1,000 is standard error is standard deviation of the sample mean. Sample mean. Okay. Okay, and for the standard error theoretical, so the theoretical is your sigma over square root of n. So this one, okay, so sigma, the value obtained earlier, this one, sigma value, okay, sigma over square root of n. Oh, what happened? What and a? What and a? Okay, this one, what and a as standard error actual. Oh, sorry. our sample mean actually incorrect object, sorry. So just rerun. Okay. So can you see here, the standard error actual and standard error theoretical, which is 50, the value of actual and theoretical value is very close. 49.71946 is very close to 50. Okay, so here I just add here. Actual standard error is the so I would like to round off our standard error actual to maybe 2 decimal places. Yeah. Okay, theoretical is okay, just run. Okay, so theoretical standard error is 50 and the actual standard error is 49.72. So this value, the actual and the theoretical value of means and standard error is very close to each other. Okay, thank you.